Thank you. So first of all, I would like to thank the organizers for inviting me to this talk. It's a great opportunity. So I'm going to talk about representations. In this context, it means that I'm looking at a signal space and I would like to find some form of concise description of a part of that signal space. Invariance is clear, whereas in this case, invariance is primarily with respect to spatial deformations, but we can also be invariant to monotonic transformations of the signal itself. So at Siemens, certainly we're looking at applied research, and in particular here we are doing computer vision and pattern recognition. So the examples that I'm going to show are primarily from this domain. So I'm first going to introduce a continuous model of this construction scheme, and then I'm going to show discrete approximations and some examples of applications for this. So we start with a simple question. How do we get from A to B? Sounds simple, but it may not be. More precisely, we know A, and we would like to find B. So let's start with a map. Everybody knows how to interpret a map, right? You have two locations. You are at A, you would like to get to B. Maybe you're describing it to somebody in a foreign city. So the simplest description you can come up with is 3 kilometers in this direction. The second kind of description may be, okay, you take this road, then you go this far until you hit a roundabout, you go about the roundabout, and so on, and then you arrive at the location B. The third kind of answer may be, okay, get to this bus station, take bus number such and such, exit at this station, and then walk the rest. So how can we structure these? The first one certainly has an Euclidean aspect to it. It's basically in terms of the Euclidean distance. The second one has a sort of a topological nature to it, because you're describing how to get from A to B in terms of the underlying signal space. The third one is somewhat functional. You're not even talking about the signal space, you're just trying to solve the problem. So in this talk we are focusing on the first two, the Euclidean and the topological. Now, an interesting thing happens when you look at spatial deformations. So again, you have your canonical map, and then it can undergo certain deformations, right? Rotation, non-uniform scaling, and in general you can have smooth deformations of the domain. This is sort of the starting point that we're looking at. Now let's look at what happens to the different descriptions under these deformations. So here it's just an example of a deformation again, and you have your Euclidean and the topological description. And certainly when you look at the Euclidean description, it doesn't fit anymore, right? If your domain suddenly is deformed somehow and you still use the Euclidean description, you're not getting anywhere. You're going way past beyond B. For the topological description, certainly you're still getting at the right location. So the topological description is invariant to smooth spatial deformations. So now, what is the connection to, in this case, computer vision and pattern recognition? So if you look at your typical computer vision algorithm, things like segmentation, tracking, object recognition, and so on, then you will find that if you drill down deep enough into the algorithm, at some point you will be relating 2 points in a signal space. This is not true for all algorithms, certainly, but for a significant large chunk of them. So this is a basic building block in building higher level algorithms. And certainly then you have deformations in true signals. So having an invariant representation instead of the Euclidean distance may be a valuable tool. So then the question is, can we relate locations practically by their topological connectedness? So this is the central promise of this work. So we want to relate the 2 points by the signal connectedness between them. We want to do this to gain an invariant representation, and we're going to do it based on one-dimensional path description. So basically we're factorizing the problem into a set of one-dimensional problems. So let's look at an example. What you see here is an object that is to be modeled, for example, for the purpose of recognition or identification. Then we choose 2 arbitrary locations on the object, A and B, and then under a smooth deformation, these locations move somewhat arbitrarily, right? Now, how is this situation typically addressed, particularly in this domain? What you do typically is you try to characterize the deformations that may happen, And then you get some data, and then you build up a model, for example, a probabilistic model of how that other location could be, where this other location could be located as a condition of all the other things you know. And that's a fairly typical thing. Certainly this, the probability density here has an extent, so you have uncertainty. That's something you would have to deal with. So how do we do it instead with the topological connectedness? First, we look at an arbitrary path between the 2 points, the curve gamma in this case. And then you can look at how the curve gamma is deformed. And then you look at the function of the image along that curve gamma. And certainly, so this is the tau, which is just the functional composition of the image and the curve. And then certainly the traces, we call them tau, are equivalent. So you can do the same in both spaces. We then say that the trace relates A and B. And it does that in the original space as well as the deformed space. And it's the same trace. Now, what do we have so far? So we have a means of relating two signal locations by the trace tau, which is just the image function along an arbitrary curve between the points. Now we have given A and B, and A prime, and we would like to find B prime, basically, given the tau. So far, this is an existential definition. So we have said this is a necessary condition for B being the proper location, but it's not a computational definition. It doesn't tell us how we do this. And this is where the complexity comes in, because in practice, we need to prove the existence of that particular trace between A prime and possible B prime. If we are able to do this, then we can identify B prime and find its location. And a lot of the work is in making this a computational definition instead of an existential definition. And I'm going to sketch briefly how we do that. So there is a bunch of problems that we have to consider in doing so. The first one is incompleteness. So I cannot characterize all points in the domain necessarily by these paths. So for example, if you look at a homogeneous region and B turns out to be in that homogeneous regions, all the points in the homogeneous regions are topologically equivalent. There is no way from the signal to tell any differences between locations in that homogeneous region. That tells you it may be incomplete. How do we solve this problem? We ignore it. It's as simple as that. There are some arguments though, so we're not ignoring it blindly, but the idea is just that in homogeneous regions, the signal is most likely not informative anyways, and we are looking at having concise representations of signals, so we don't care too much about homogeneous regions. The second problem is ambiguity. One other thing that may happen with signals is occlusion, for example. So if part of the path is occluded, then it may be that the same trace leads to different locations, not only from A to B, but also to a B not, which is, from our understanding, the wrong location, basically. So how do we avoid this situation? It's fairly straightforward. Instead of one path, we just use a multitude of paths between the points. And then, basically, the impact of possible occlusions is minimized because there may be a path basically around that occlusion. So if we go to the extreme, we would do this over all paths. That would be a complete characterization of the domain. And here you can see most of the paths basically end up at B, or only very little ones end up in B not and other locations. So the idea is that most of them will end up in the right location, even under occlusion. The next problem is that we have an uncountably infinite number of paths, certainly. Yeah, so that's, from a computational perspective, a significant hurdle. So how do we address this? We discretize the path descriptions and we limit their length. And that gives us a finite space to deal with, which makes it computationally. So there is various ways of discretizing it. And these are all approximations. I'm not going to go into much detail, but just showing the general scheme. So here you discretize the space. So your curve is now only in a finite set of nodes. And then you can talk about the relative spatial relationship between those nodes. Now, the last problem is that the image information, the image profile information, is not robust. So if you just look at the function along a path in the image, you have practical things like noise. And noise is exaggerated if you're only looking at very little information. So we may be interested in looking a little bit more information, basically to counter that noise. And we are doing this by basically looking at a small neighborhood around the path and coming up with some way, some means of describing the texture in the small patch. Certainly that breaks your invariance to smooth deformations, because now you're looking at small neighborhoods. But you can do this in an invariant way as well, and if these descriptions are invariant, then the whole description is invariant. Then you have basically labels, so we quantize, again to make it computationally, to have a finite space. We quantize the texture in these nodes. And then putting everything together, this is basically our discrete model for the trace. It's a finite sequence of label relationship pairs, and it restricts the location of B given A, and the same for B prime and A prime. So now certainly we have made approximations. So what do these mean? First of all, the resulting discretized and quantized algorithm is only quasi-invariant. It's ill-defined, but it's only robust to deformations. It's not fully invariant anymore to smooth deformations. That's a compromise that we have to live with, but it's a reasonable thing still in many applications. We have to choose parameters, so we need to do empirical evaluation and so on. It turns out that we can have a tunable trade-off between the invariance of the representation and the information content, in a sense, of the representation. So we can either be more invariant or capture more information of the signal, depending on what kind of application do we have. This is a very valuable thing to have, because you have a little slider, basically, which you can tune according to your requirements. Here, I'm going to just briefly talk about two choices. One is rotation invariant, meaning we are entirely invariant to rotation. And one is rotation sensitive, so we're only quasi-invariant or robust to orientation. So just briefly, how does it look computationally? It turns out then, given this discretization, it maps to a graph problem, which is always nice because we can handle graph problems. And it's just about proving the existence of attributed paths in a graph. Here you can see the condition. This is basically if this condition is fulfilled for particular nodes, then you have proven the existence. You have the graph adjacency matrices, basically, which encode all the information that you get from the discretization. And A is very sparse. The adjacency matrices are very, very sparse. They are large, but they're sparse, so you can efficiently compute, basically, and you can do all sorts of tricks. Now we are at a state where we can practically relate two locations where we have certain invariance to spatial deformations when we do so. And earlier, I've already mentioned this is in parallel, basically, to the Euclidean distance. Now I'm going to show what can we actually do with it practically. And that brings me to the Huff transform. I won't go into too much detail due to time. Suffice to say, the Huff transform is a fairly common method in computer vision and pattern recognition for solving things like shape detection, shape tracking, and a whole lot of extensions. And the vanilla definition of the Huff transform is fundamentally based on the Euclidean distance. So it's an algorithm where you relate basically the shape of objects, so I won't go into too much detail, but you do this via the Euclidean distance. And then if you have deformations, the Euclidean distance goes haywire, because it's not invariant to smooth deformations. So now the question is, can we just take that algorithm, take out the Euclidean set relation as a basis building block, and put in the trace relation instead, and don't change anything else about the algorithm. It's purely a plug-in method. That's what we're going to do. So if we want to represent this object, we choose an arbitrary location on it. It doesn't really matter what, so here it's just roughly the center. And then we're looking at any other point on the object and relating it to the center point via the traces that I've introduced. And we do this for all possible points on the object. So again, this now is basically almost complete characterization of the object in terms of the trace definition. And I can computationally handle this. So if I get a new target pattern, let's say, where I want to find this object, then I can go through all locations and question, can this location be described in terms of its neighborhood by these set of traces? That is the general scheme of using it for example, describing objects. So I won't go too much into detail here, perhaps let's skip a little bit. So I'll show two applications very briefly that are computationally exactly similar, but the higher level methods differ a little bit. So the first one is matching image patches. That's a very low level operation. It's more to illustrate what's going on in terms of invariances and capabilities of the model. And then the latter one is a more practical application, that of incremental visual tracking. So you have a video sequence, for example, of people walking around, and you would like to track them. That's a generic problem. So the first one, we are looking at the performance under a set of deformations. These are synthetic, so we take data and then perturb it. And the perturbations are, for example, noise, rotation, scale, occlusion, where part of the domain is occluded by distractors, and then certainly smooth deformations. And then we can look at the performance of the model in the problem of patch matching. So what you see here, this is, for example, for the perturbation of rotation. So you apply a rotation, and then you try to find, again, your reference patch in the target setting. And then you can ask, up to what rotation can I still do it? And as I've mentioned, we have a rotation sensitive and a rotation invariant version. And this is the rotation sensitive version, so you see it sort of tapers up. And this is the detection rate. So this is a measure of the performance of how good can I still find the object or the image patch or signal patch. And here you have perfect performance at 0 degrees because you're comparing exactly the same thing. But if you rotate one slightly, then the comparison becomes harder and harder and harder. And certainly the rotation sensitive one tapers off. So at something like 30 degrees rotation, you're only able in half of the instances to actually find it again. The rotation invariant has perfect performance over all rotations. That is just because it is rotation invariant. So the performance is uniform over there. Then you can look at noise, for example, and you can look at occlusion. And you can see one interesting thing, for example. So again, here you have the sensitive and the rotation invariant version. And you can see that the rotation invariant version is slightly worse, and it's significantly slightly worse than the rotation sensitive one. And that is just because I have more invariance in the rotation invariant one, meaning I lose something. I can't have both. And what I'm losing is a little bit of performance in actually solving the task. And here this shows the slider, basically, where I can tune my representation based on this construction scheme according to these requirements. If I know that I don't have any rotation, then I don't need a rotation invariance. Then I just design it to be rotation sensitive, and I have better performance. That's the idea here. So I'm going to show now a couple of examples related to visual tracking. So you have a video sequence, and then you set a point or a bounding box, and then you would like to track basically that object through the video sequence. And there is the ground truth will be shown in white, the trace method that I've presented here in green, and the state of the art on the sequence in red. And the thing to look out for is that you have a lot of deformations. So you have illumination change, for example. When he walks under the light sources, the illumination changes dramatically. You have shadows, self-shadowing, you have self-occlusion, you have out-of-plane rotation, and so on. And these are all very challenging real-world signal deformations. Some of them are smooth deformations, some are definitely not smooth deformations. So he takes off the glasses, for example. There is no simple function to express that. And you can see the green one stays nicely on the tip of the nose. So let's. I'm just going to briefly perhaps show this here. So here you see this is a pose sequence, but the idea is to look at occlusion. So now basically large part of the signal is going to be occluded. Here, half of the relevant signal is included, but you're still spot on, basically. And then there is out-of-plane rotation and so on. And our representation is a principled construction scheme, so we can also explain particularly why this behavior is as it is. So we can explain the performance, which is also an important practical consideration. So now we've compared this with the state of the art on a certain data set. And the performance is already somewhat saturated on the data set, but we are able to beat a whole lot of the state-of-the-art methods. And it's important in that particular domain to understand that practically all the state-of-the-art methods, they use machine learning. So they basically have a data-driven automatic mapping of the algorithm to the best performance. And we are not using any machine learning. So this is only motivated from first principles. And the performance comes just from careful considerations about what the signal deformation means. And then we can certainly put machine learning on top of this if we choose to do so. Now, to really investigate basically how the invariance properties of our solution influences the performance. We did a simple experiment, again in incremental visual tracking. So incremental visual tracking means I start somewhere and then I track the object through the scene, and while I'm tracking it, I continuously update my model on a short term with something like exponential forgetting. So I'm forgetting what is in the past, but I look at the recent history and then I model that object. So I can model the evolution of the object throughout the video sequence. Now what we did here was to skip all that. So we just take the first instance. We only have one sample basically to track the object. We're not using any model building. And then we are comparing with, again, the same methods. And it turns out that we can still beat 4 out of 6 state-of-the-art methods significantly. Yeah? And they're using incremental updating, so they can use much more data than we can. So this is definitely an argument for the invariance. I would also like to visualize that a little bit. What you're seeing here on the left side of the top frame, this is just a video sequence, and we marked the bridge of the nose of the person in the first frame. And this is exactly the data that we're using. So we're only using this particular frame. And on the right side, you see the likelihood surface. So this is the output of the algorithm, basically, which tells you for each location in the domain, how likely is it the correct location. And then when you look at the video, so you see, again, a lot of deformations. So the turning of the head, that is out-of-plane rotation, and so on. And the important thing to look out for is basically the compactness of the peak in the likelihood function over the whole sequence. So here you have non-uniform deformations of the face when he makes grimaces, takes off the glasses. All that changes your signal in comparison to the original signal. And so here you see it weakens a little bit, but we're still spot on. Certainly you can make it fail by just turning around, right? If I see only the back of the head, there is nothing I can compare with, right? This is the limit of something like this. Okay, and I can just zoom in basically. This is the reference patch that we are using, and then on the right you see the detected patch. And it's important to notice how this point stays on the bridge of the nose. Really, it is in the correct location. If you look at the output of your typical tracker, that point would shift according to the bounding box, basically, because you're tracking the whole object, whereas we are tracking a point. Yeah. So even if he then turns a little bit, here you have scale. It's not too much, but it's enough to fail in certain. So here, for example, if out of plane rotation and you're still on the bridge of the nose. Okay. Okay, so that brings me already to the conclusion. Just summarizing very briefly the trace model as a construction scheme for invariant representations. And I've only shown one particular discrete instance. There are various other ways to discretize the same model, which will yield vastly different algorithms with different trade-offs. It's a white box model, so we can analyze it fully. We can understand fully what is going on. There are no hidden parameters, and the parameter space is fairly small. It's a plug-in for the Euclidean distance, so you could take, apart from the Hopf transform, you could take another algorithm, plug it in, and see what happens. It factorizes a complex problem into one-dimensional problems. As I mentioned, you can derive various representations. It's tunable, it's efficient, and so on. And one more thing to note is that the notion of dimensionality doesn't affect us too much because we are factorizing it into a set of one-dimensional problems. So a similar thing would apply not only for two-dimensional spaces that I've shown here, but also three- and n-dimensional spaces. The fact that you're relating locations by paths is still one-dimensional. You can certainly talk about higher level manifolds in terms of the path description and relate points by planes lying between them and two-dimensional and n-dimensional manifolds, but that becomes computationally very challenging. So thank you for your attention. Any questions? Okay, so the question was, how do we compare between a reference and a target pattern given our representation? So similarly to the Hopf transform. So basically we take a reference pattern, which is a location, and then we describe this location in terms of the traces to all other locations in a certain neighborhood, which is defined by the finite length. And that is our description. So we have basically a set of values which describe these paths to all other locations, and that defines that point. Now, if we want to find that point in a new location, we do something similar. Like it's exactly the Hopf transform, so we vote. So we look at a particular location, and then we enumerate all possible traces to that location, and if they match, we increase our vote. And if many matches, then it's most likely the right location. That is exactly the likelihood function. So if you have n reference traces and you find n of them for a target location, then your likelihood is 1, basically. You're voting over paths, exactly, implying that you have to enumerate all of these paths, which is exactly the graph problem that I showed earlier, basically finding those attributed paths. It's just, computationally, it's just a set of matrix multiplications. You can do it a little bit smarter, given the priors that you have here, but that's what it comes down to. So you have a variety of, so the question is, right. So the question is, why would it fail for incremental tracking if you have, for example, out-of-plane rotation where part of the object is occluded? This is exactly what incremental tracking is doing, basically. Where you try to characterize the object by a model and then update that model temporarily throughout the tracking of the video sequence. It's certainly an ill-post problem because you don't know, in certain situations, you don't know what is still the object and what is not the object anymore. So you have to make a lot of assumptions about the object. What I've shown here, basically, for the incremental tracking based on the trace model, we have a very simple scheme of updating the model. It's very trivial. There is little intelligence into it. So certainly you could improve that significantly by doing it. And this is what a lot of the work in tracking is actually about, how to update the model and how to do the forgetting, and what does it mean to forget past data, and when do you forget it, and all of these details. There is a lot of engineering. We skipped that and did a very simple model. And we just rely on the invariance, basically. So if we move out of plane, up to a point that's a smooth deformation, up to the point where I don't see the original information anymore, then it's something entirely else, occlusion, basically. So eye tracking typically is a high precise application, right? So you're interested in things like gaze estimation or perhaps psychological studies, biological studies. In print, for both eyes. So we do practical, so the question was, can it be applied to eye tracking? So we do practical things, right? And so the practical answer is, in this case, you have a lot of prior information. You know that the eye is roughly ellipsoid. You know somewhat what the joints in the eye are. They're complex, but you can model that fairly well, right? So it may be easier and more practical to do that. Certainly you can do it agnostically in that sense and just say, okay, moving the eye means you have some sort of smooth deformation. And then certainly you can do that. And if you have a particular prior knowledge about the types of patterns that you have, then you can even put a learning algorithm on top of it or some further characterization of that particular input space.
Thank you.
Thank you.